We'll now come on to solving linear differential equations with constant coefficients, giving the full-scale version of such an equation. And for example, let's take the equation d2y dx squared plus v dy dx plus wy equals some function of x. And this is a typical second-order equation of the type under discussion. V and W are constants. Now, first of all, let y equals h of x be the solution of the homogeneous equation, the homogeneous equation being the left-hand side of the given equation equated to 0, and let p of x be the particular solution of the equation including the right-hand side equal to f of x. So, just differentiating, we'll find then that the second differential of p plus v times the first differential of p plus w times p is f of x. That's just by the definitions we've just given. And for the homogeneous equation, second differential of h plus v times the first differential of h plus w times h itself will equal 0. All right, that's what we have supposed. Now, let t equal h of x plus p of x, so that dt dx is dh dx plus dp dx, and d2x dt squared is d2h dx squared plus d2p dx squared, which is written there. So now, substituting t into the original equation, instead of y, on the left-hand side, we'd have d2t dx squared plus v dt dx plus wt equals h, the second differential of x with respect to t, plus v times the first differential of x with respect to t, plus w times h of x itself. And then similarly, down here for the p, the second differential of p with respect to x, plus v times the first differential of p with respect to x, plus w times p of x. Now, the first line there, this one here, is equal to 0 by definition, and the second one was equal to f of x by definition. And 0 plus f of x is still just f of x. So, replacing y by t gives a full solution to the original equation. H of x is called the complementary function, and w is called the particular integral. And as we've just seen, the complete solution of the differential equation is found by adding the complementary function and the particular integral. Right. Now, this holds for equations of the type under review for higher orders as well, and the proof is pretty well exactly the same, just a little longer. So I'm now going to do a worked example of a second-order equation of the type we've just been talking about. And here it is, d2y dx squared plus 8dy dx plus 15y equals 2x plus sine of x. Now, the auxiliary equation is the equation of considering the left-hand side equal to 0. This is what we did at the very beginning, and replacing the differentials by m squared and m, we get the following: m squared plus 8m plus 15 is 0, which factorizes as m plus 5, m plus 3 is 0, so m is minus 3 or minus 5. So we're down to here. And the complementary function will be this expression here, y equals ae to the minus 3x plus be to the minus 5x. That we've covered in a previous episode. Now, the particular integral comes next, and I've remarked here that this is usually where most of the work lies. So, we want to try the y equals px plus q plus r sine x plus t cos x, because this expression here has to be a generalization of the one that we have been given, in other words, 2x plus sine x. Now, if we differentiate that, we'll get p plus r cos x minus t sine x, and differentiating again, we'll get minus r sine x minus t cos x. We now need to substitute back into the original equation, and we'll get this lengthy expression here. Minus r sine x minus t cos x plus 8p plus 8r cos x minus 8t sine x, then plus 15px plus 15q plus 15r sine x plus 15t cos x, and that has got to be the very identical of 2x plus sine x. And then equating the coefficients of like terms, we will get 8p plus 15q is 0. That's this one here. 14r minus 8t equals 1. That's equation number 2. And 8r plus 14t equals 0, which simplifies slightly by dividing through by 2 to 4r plus 7t equals 0. And last of all, 15p is 2, which makes p equal to 2 over 15. So we got that far. From these equations here, and just using basic algebra, we'll get p equals to 2 over 15, q equals to minus 16 over 225, r equals to 7 over 130, and t equals minus 2 over 65. And the general solution will be, of course, the complementary function plus the particular integral, and this will then be y equals ae to the minus 3x plus be to the minus 5x plus 2x over 15 minus 16 over 225 plus 7 over 130 sine x minus 2 over 65 cos x. And that is the complete solution. Thank you for listening.